Hello, everyone. It looks like I was muted and I didn't realize, so I apologize for the mistake. But nonetheless, I'm going to start at the beginning because I'm really pleased to welcome everybody to this afternoon Department of Earth, Planetary, and Space Sciences, Exploring Dynamic Planets from Surface to Core webinar, featuring Professors John Arnaud, Carolina Bertelloni, Livgo Bertelloni, and Mackenzie Day. My name is Miguel Garcia Garibay, and I'm the Dean of the Division of Physical Sciences, and it is a pleasure to welcome you to what I know will be a very interesting program. In my role as Dean of the Division of Physical Sciences, I have the privilege of working very closely with many faculty in all of our departments. Physical Sciences is a division rich with education and research excellence, which has had an enormous impact in the world through its 6 departments, which in addition to Earth, Planetary, and Space Sciences includes the departments of Atmospheric and Oceanic Sciences, Chemistry and Biochemistry, Mathematics, Physics and Astronomy, Statistics, and the Institute of Environment and Sustainability. Now, the Department of Earth, Planetary, and Space Sciences strives to understand and protect our home in the universe. The department scientists delve deeply into our very own Earth and look to planetary bodies well beyond our solar system to learn how planets like ours formed and evolved. EPSS scientists have detected an ocean on Jupiter's moon Europa, discovered the Kuiper Belt at the outer edge of our solar system, and lead many NASA spacecraft missions. Our dedicated faculty also study Earth's most ancient rocks and life forms, earthquakes, earthquake hazards, and climate changes. But today we will hear from 3 outstanding professors from EPSS whose work interacts with each other in interesting and natural ways, working from the very innermost core of our planet to the surface, and even other planets, such as Mars, which has been in the news quite a bit recently, thanks to the successful landing of the Mars Perseverance rover. As an aside, it gives me great pride to share that the deputy principal investigator of one of the NASA's rover experiments on Mars is our very own EPS professor, David Page. Professors John Arnaud, Carolina Livgo Bertelloni, and Mackenzie Day manage 3 state-of-the-art facilities at UCLA that each have different focus, but together enable unprecedented capabilities for understanding and quantifying the vast range of fluid processes responsible for shaping and controlling planets. Now, it is my pleasure now to introduce our first speaker, Professor John Arnaud. John will start us off at the core, sharing how fluid dynamics on spinning planets are responsible for generating jet streams and vortices in their atmosphere and magnetic fields in their molten metal cores. John, the floor is yours.
Okay, thank you so much, Miguel. Start my video. Oh, I think I turned off my video. I'm going to share my screen. And I'm going to start this. Okay, thank you so much. Today I'll be talking about the effects of rapid rotation in spinning planetary bodies. That is what we study in my lab in EPSS. And so the focus is, as Miguel said, largely on jets and vortices, as you see in this image on the left for Jupiter, and for one of the other large-scale planetary structures, magnetic fields, which are generated in the liquid metal cores in the interior of planets. And what I'll focus on just today is Earth. And so we'll work our way inside Earth. The inner half of our planet is largely composed of iron. The innermost third being solidified. The pressure is so strong that the innermost part of the planet is actually a solid iron. And then the outer 2/3 is a liquid iron. And the scale of this structure, the size of the core, is about 3,500 kilometers in radius, which means the core of Earth is about the size of Mars. This core is inside the mantle. And the mantle really controls how energy and heat transfer out from the core. And so it's locked away inside the mantle, and the mantle controls how much energy is released and how vigorous are processes within the core. Okay, so one of the most interesting processes within the core is that there's a lot of fluid motion in the core. And as this fluid moves around, some of the energy from that motion of this liquid metal is transformed into magnetic field energy. And that's how we generate our geomagnetic field that shields the planet from the ambient space weather all around us. Okay, what can I say about this? Well, the magnetic field's typically aligned rather well with the rotation axis of the planet. So the North Pole that we're spinning around also is well aligned with the pole of our planet's large-scale magnetic field. It's been there a long time, about 3.5 billion years, maybe older. People are now saying maybe 4 billion years, but that's a point of rich argumentation. And maybe most importantly, or most interestingly, is this magnetic field flips now and then. Every about, let's say, 300,000 years, the field will be pointing one way, and then the magnetic field will say, no, I want to be a magnet pointing the other way, and it flips. Okay, how all of these things occur are really open science questions. I'm just, for fun today, going to focus on explaining the axial alignment of the magnetic field. Why do our compasses work? And so first I want to explain, well, what's driving the motions in the core? So what's driving the motions is convection. And what that means is we can do a little experiment. We can do it with water. I put water in a tank here. I put some green dye at the bottom, and I put a heating plate below. And when I heat from below, the fluid near the bottom becomes buoyant. It becomes less dense, and it tends to float up. And you can see that. Great. I took a little movie with my phone. And there we go. There's convection. That's what's occurring as well in Earth's outer core. Now here, the convection is being driven because the inner core, this solid inner part, is actually growing over time. It's growing from the inside out. And as it does so, it releases heat, and it releases kind of blobs of light compositional elements. So there are two forms of buoyancy being given out. There's a gravity field that's radial, it's a planet. And so we could think of porting our little experiment to the core, and we might expect to see, boom, there's motions coming off the inner core being driven as it grows. Now, I didn't account for rotation, and I didn't account for the magnetic fields that are there either. This is a very cute movie, but it doesn't look like these motions, if they somehow generated a magnetic field, like those motions would be aligned with the rotation axis. So let's see if we can figure that out. So yeah, why is the geomagnetic field aligned? And so let's do a little better experiment than the one I did before. Now we'll do a cylinder of fluid, and we'll put it in my lab, and we'll light it from behind and look at the fluid that we're heating from below and cooling from above. So we're making it, again, have this buoyancy-driven convection. And first, we'll take a movie with it non-rotating. And if it's not rotating, the motions are a mess. And so what we're looking at here is the pattern. Basically, this is called a shadow graph, and it shows the pattern of motions in our tank. It's a little distorted by the shape of the cylinder, but you see it's just a mess. Now, if we do the same experiment and rotate, again, planets spin really fast. Then all the motions line up. They become, is it still buoyancy-driven convection, but now we get little tornadoes, little whirlies, and they all tend to align with the rotation axis along that axis. And we see that in supercomputer models as well. This one by my colleague Thomas Gastine, the lab movies by my grad student Jula Bate. And in both cases, you have this alignment. So it's some zeroth order. So it's some simplest way. We can say that the alignment of the magnetic field with the rotation axis is due to the fluid mechanics. And the fluid motions line up with the rotation. They act like little spinning tops. They all align. And they generate magnetic fields that on average somehow align. Okay, I didn't actually explain how that occurs. I've simply said that that somehow happens. To explain how that occurs, we need to make much more advanced models. So in my lab at UCLA, we have a bunch of experiments that we then couple to supercomputer models. And in these, we simulate pieces of a planetary core or a planetary atmosphere to understand how do we get these magnetic fields to come out of just what would appear to be fluid turbulence, a mess. The same thing with jets on Jupiter and big vortices. How do we get them? We try to build them in the lab and couple them to theory and numerical models. And so we have advanced tools. These are unique devices. The one on the left is actually the world's largest rotating convection device at this time. The one on the right is the only liquid metal rotating magnetoconvection experiment in the world. So therefore, it's also the largest. How do we make measurements? We use optical techniques, we use acoustic techniques, and we do advanced thermometry as well. All of this is world unique, and all of it actually rather both physics intensive and engineering intensive. In addition to doing quantitative measurements to understand how planets work, we've also been trying to get these ideas out beyond just the science community and to a broader community. So for about the past 12 years, my lab's been generating outreach videos. And we have a little under 800 subscribers to date. We've had about 150,000 views. And we're trying to make movies that are useful for classes and useful for people simply interested in understanding climate and planetary and stellar fluid physics. In addition, we've actually built devices whereby people can do these experiments on their own. So this is another project we're doing for outreach, and it's called the DIY-namics project. And here we use a Lazy Susan, a Lego motor drive, and we create these kind of aligned structures and rotating fluid flows that you see kind of like what you saw in the lab experiments, or we can do different experiments where we simulate climate in Earth's atmosphere. And we can also do experiments in these little tanks where we make vortices like we see on Jupiter. We're trying to get those out to classrooms around the country, eventually around the world. When we can't do that, we're happy to take our devices to outreach events. Again, we want to get everybody doing science, everybody thinking STEM. And so with that, I'll thank you and I'll pass it back to Miguel. Thank you again.
Well, thank you very much, John. That's really fascinating. That's amazing. Thank you.
How do I unshare? Give me one sec.
There you go. So we will next travel from the hottest regions of our planet a little further up to better understand how the dynamics of Earth's deep interior can exert control over sea level changes. We will hear from Professor Carolina Lisgo-Bertelloni, holder of the Louis B. and Martha B. Schlichter Chair in Geosciences. Carolina, please.
Thank you very much, Miguel. Let me share my screen. And so hopefully that's visible to everybody. So thank you, John, for that introduction, because you've introduced your first talk, because it introduced some really important concepts. Rather than just sort of really go from the core all the way up, sort of step by step, I'm actually going to talk about the consequences of fluid motions, not in the Earth's core, but in the layer right above, which we call the mantle. And I'm going to do so by illustrating, how it might affect sea level. Now, we're all very interested in sea level change in the future, because it's one of the sea level rise is one of the consequences of climate change, of global warming. And so it's illustrated here in this picture right here with the sea level rise. We have years in this column right here from 100 to 8,000, the sea level rise that is expected, and a series of cities and their elevations. And on this column at the very far right edge, you look at the total contributions to sea level from the different ice sheets, Greenland, Antarctica, and so on, and some maps of what the Earth might look like if there were this amount of sea level rise in 8,000 years. And as you can see, even 1 meter of sea level rise is quite significant. Even 20 centimeters of sea level rise is quite significant, because in fact, 84% of the land above sea level is actually pretty much at sea level. Now, so what you'll notice though, is that there is a time scale, right? There's something that we might expect in 100 years, and there's something that we might expect in 8,000 years. So time scale of the sea level rise is also important. So if we go further back into the geological past, right? So this is about 230 million years ago. This is a reconstruction of what the Earth might have looked like. And so what you see in the sort of green and brown is the position of the continents back then. And in the deep blue and the lighter blue is the presence of the sea, both shallow seas and deep seas. And what you can see is that vast chunks of North America, Eurasia, overall, Africa, and not so much South America were completely flooded. London, where I used to live until 3 years ago when I moved to UCLA, looked like this, right? And the time, this was a time when sea level was probably 100 meters to 120 meters higher than it is today. But this is now a very different time scale than the 8,000 years. It's a time scale of 250 million years. In fact, the climate was so different that this is what London looked like, and I can assure you it does not look like this today. Okay, but how do we understand that sea level rise? And how do we try to explain it in terms of what's happening inside the surface and not just sort of the consequences of global warming? Now, the first thing is that to know how much sea level it's going to rise, you actually need to know the land elevation really well, because sea level will be defined with respect to the land elevation. So in this cartoon here, what you see is a very exaggerated shape of our Earth, right, of the land above sea level in this green line. And then the sea in this sort of ellipsoidal blue that you see here. And so the intersection, right, of the land and the sea, that would be sea level. But in fact, you know, in terms of this shape of the Earth, of the sea level, actually, it's roughly the shape of the Earth that it's in hydrostatic equilibrium, right? And that shape of the Earth, which is the gravitational potential of the Earth, it actually determines sort of how the Earth is going to move, sort of, you know, the surface of the Earth might move back and forth. But what it's clear is that to understand, you know, the sea level rise, we need to understand the shape of the Earth and the elevation of the Earth. So what do we know about the elevation of the Earth? We actually can measure it really accurately, right? This is a picture at less than 1 arcsecond of the topography and bathymetry of the Earth. Bathymetry meaning the elevations under the sea, and topography, of course, the elevations of the land in which we live, on which we live. And when you see that this is a very complex picture, right? Not only do we have a bimodal, right, a distribution of topography, land and ocean, sort of, if you want, elevated and deep, we also have enormous amounts of deformation and different things going on at the surface, which are all related to the movements of the surface. So how do we understand the contributions to topography that you see right here? Okay, well, this is what I'm going to try to illustrate in this cartoon. And this cartoon, what you see is a cross-section of the Earth from the surface to the core mantle boundary. And here is the core. John's core is right here, obscured by everything else. The core mantle boundary being the boundary between the core that gives rise to the magnetic field and the mantle above. The mantle above, unlike the core, is not partly liquid and partly solid. It's actually completely solid, okay? And that's a really important distinction. It's not made of iron, it's made of rocks, right? So mostly silicates, okay? So what gives rise to the topography of the surface, right? You could say just plate tectonics, but in fact, you know, it's a bit more than that. So if you have a continent that's elevated above sea level, there are contributions that are related to how thick the crust at the very top is, okay? How you're forming a mountain. And then the other thing that it's related to is these arrows that I've illustrated here in blue and yellow, which are related to the motion inside the interior. So flow in the mantle, that is either up or down, actually gives rise to large scale topography at the surface, which explains not only a general elevation of continents, but actually also explains past flooding of continents and also partly the shape of the Earth. But I just told you that the interior of the Earth is solid. So how can it move? Well, it turns out that if you wait long enough, just about everything is going to flow. And if it flows, it can give rise to convection, just like what John showed you, same as driven by buoyancy, except that instead of lasting seconds, it lasts millions of years. Okay, so this flow in the earth generates topography at the surface. By generating topography at the surface, it changes the distribution of mass at the surface. Where there was air, there might now be land. Where there was rock, there might now be sea. And as a result, it changes the overall shape of the earth. Okay, now these are the kinds of things we try to study in my lab, which is to how do I generate flow inside a material that it's very, very viscous, like the interior of the earth, and how can I measure those currents of flow so that I can see how much deformation there might be at the surface generated by this flow. And this is what my lab looks like. Not here, my lab here is slightly different. This was my previous lab in the UK. Okay, now you can ask, does it matter that that flow in the mantle is generating elevation at the surface? Well, let me illustrate it here by something by South America. We have map of South America here. This is the elevation of South America in the colors and the color bar here. Okay, as of right now, as of today. And then the contours that you see here in this area of Peru, in this area of Chile and Argentina, are actually contours of the topography generated by flow in the mantle. If I subtract that topography generated by these motions in the deep interior in rocks from the actual topography of South America today, I see that there are two regions, one right here, which is this circle here in Peru, and one right here, this circle here. And if you can see where this was this slight elevation here, it's completely gone here. And over here also, the elevation has changed. So the elevation of South America would be completely different without this topography. And then again, you can ask, does it matter? Well, it does. And in this complicated figure here, it's how it does, okay? The Amazon River did not used to drain in the Atlantic. The Amazon River used to drain in the Northwest Pacific, as illustrated by this picture on the left, where you see this blues and so on. And these arrows were the drainage of the Amazon River. When some flow in the mantle happened, so it elevated South America, which was these sort of contours that I was showing you here, it actually lifted the Andean Cordillera right here. It lifted the whole area so that now the Amazon could no longer drain to the Pacific Northwest, but started draining internal to South America. So much so that, as you see in this cartoon here, it filled out the basins with sediments carried by the river until it completely filled the basin and put all the outflow of the Amazon River into the Atlantic today. So the motions of the interior of the earth happening over millions of years can actually change the drainage of big rivers like the Amazon and even other rivers. And that is because it changes not just the elevation, but the distribution itself. So now you can ask, if we go back to the question of timescales, whether it would matter for today, okay? And the answer is yes, it actually matters also for today. Why? Because these motions from the interior that change the shape of the earth, that are actually changing the distribution of mass at the surface, actually change the response to, say, the melting of an ice sheet. And I'm trying to illustrate this here with a paper that came out a few years ago, where that if you try to melt the Greenland ice sheet and you calculate the gravitational response to that melting, in the presence of flow in the mantle, what you would actually get is a gravitational pole of attraction that would be centered in Washington, DC, kind of poetic justice. And if you actually try to look at the effects on sea level rise, you wouldn't feel them in Greenland. You would actually feel them much closer to and much more deeply in the eastern coast of the US. And that it's all due to the presence or absence of flow in the mantle that elevate or depresses the continent. And with that, we can pass it on to another form of deformation that is not related to water, but actually to air. Thank you.
So thank you, Carolina. That's really fascinating. So indeed, now that we have heard about the core and Earth deep interior, Assistant Professor Mackenzie Day will take us to the surface, but not just of Earth, but Mars actually. Mackenzie's talk will explore how dunes develop complex patterns that can tell us about the weather and atmosphere in any planet. So Mackenzie, please go ahead.
Excellent. Thank you for that introduction. And thank you everyone for being here today. Today, I'd like to talk about my group's work looking at dunes on Earth and dunes on other planets. So hopefully all of you have seen a picture that looks something like this, and you're familiar with dunes in general, and you've seen these sort of beautiful mountains of sand with curves that form in exotic desert locations. But dunes are actually very common on Earth, and they form very close to home. This is a picture from Death Valley National Park, where I was with my students yesterday, actually doing some research. So we want to understand how these systems form because fundamentally dunes represent that surface-atmosphere interface. We've got turbulent winds mixing our atmosphere, but those winds are transporting sand across the surface, and dunes are a really great representation of that interaction, and that lets us understand how the atmosphere and how wind on Earth and on other planets is influencing the landscape. And in addition to the science, a major goal of EPSS is to understand and protect our place in the universe. And so dunes also influence people. There are two situations here. On the left, we have two pictures from a small town, Waldport, Oregon, a small coastal town that was essentially buried by a dune field in response to a couple of large storms a few years ago. And you can see here that it looks like there are drifts of sand, much like you would see snow drifts in the Midwest. But unlike snow, sand is much more difficult to get rid of. It doesn't melt, it's much heavier. And so there was a lot of damage done in this particular storm as a result of these dunes coming in. And then the two pictures on the right here are aerial images of Nouakchott, Mauritania, the capital city of Mauritania. And in the lower picture, you can see this large dune field is actually encroaching on the city itself, and it's slowly covering whole city blocks with large piles of sand. And then at the outskirts of the city, you can see another aspect of the dune field here, where these dunes are migrating from left to right, and they're covering fields. So they're disrupting the agriculture, they're disrupting the city itself. So we work to study and understand these dunes so that we can look at the fundamental physics, but also so that we can plan and mitigate these hazards to populations of people. So how do dunes form? What is a dune? What do I mean when I say dune? Well, fundamentally, dunes are organized sand accumulations that develop in response to wind. So a dune is a pile of sand that develops, and then as that dune continues to develop and grow, what happens is you have sand on the upwind, or the Stoss side, gets blown to the top of the dune. It accumulates at the top of the dune and then avalanches down the lee, or the downwind side. And so you have essentially a conveyor belt of material where sand is being lifted to the top of the dune and then down. And then this process happens over and over again so that your body of sand just sort of marches across the surface. And oftentimes we think of dunes as forming in isolation, that there's only a single dune, but that's not really realistic. We'll see pictures in textbooks that look like this, with your dune having a steep side and a shallow side and interacting with the wind, but you almost never see a single dune in nature. Instead, what you see are fields of dunes. So here's 4 different examples from different parts of Earth, different continents forming in very, very different settings, and they all form fields of dunes. There are groups, and if you look at these pictures, every single one of these dunes is interacting with another dune, and they make these beautiful patterns that are very, very consistent across totally different environments. Some of these are high alpine deserts. Some of these are coastal systems. And so one question that comes up is how different can these environments really be? How many different environments can support dunes, and how far can we push this idea that this pattern develops in a wide range of systems? So these 4 examples are all from Earth, but dunes have been observed all over in our solar system. We've seen dunes on 6 different planetary bodies. We see them on Earth, we see them on Mars. Venus also has dunes. Titan is the largest moon of Saturn. It has beautiful dunes. Pluto, there were dunes identified on Pluto, and then Comet 67P. Even though it doesn't have an atmosphere, it has dunes. So there's something really fundamental about surface-atmosphere interactions that's developing these organized sand accumulations on all of these different bodies. And across each of these systems, you see this same characteristic, well-organized pattern of sand. So dunes are fundamental to our solar system and to surface-atmosphere interactions. And what we do in my research group is try and look at these patterns and understand from the patterns what's going on with the wind in these different environments. Now, saying that is obviously easier said than done, and there are some practical difficulties to that, right? We don't have very many wind measurements on Mars. We don't have any wind measurements on Titan or Comet 67P. So we can use a lot of different strategies to tackle these big questions of how do we understand different dune systems. So one thing that we do is we use small systems that we can see. Here's a time-lapse video of a backpack, and you can see the wind is going from left to right, and there are some ripples that are developing and migrating. And we can look at the pattern of ripples and see how the turbulent wind is interacting with this backpack obstacle, and then a wake forms behind it. So the pattern reflects that wake, and we can use these kind of smaller scale patterns to understand bigger scale systems on Earth. This is the Ibex dune field where I was yesterday with my students studying the large scale processes of the dunes there. And then we can understand even bigger systems. We can use Earth and what we see on Earth to understand Mars. So trying to connect all of these different pieces to understand dunes at a fundamental level is a big target of the work that I do here at UCLA. So let's talk about Mars. Some very exciting news is that somewhat recently, Curiosity, the Mars Science Laboratory rover, visited for the first time an active dune field on another planet. So this is a picture taken by the mast camera on the Curiosity rover of the Namib dune on Mars, an actively migrating dune. It migrates about 0.5 meter an Earth year, so it's slowly coming towards us in this picture. And this is the downwind side, so we're looking upwind. And one of the really exciting things that we've learned from Curiosity and from studying dunes and sand on Mars is that it's much harder to get sand moving on Mars than it is Earth. But once you've started it moving, you can keep it moving for a much longer amount of time. Sand on Mars will just kind of continue to bounce because the gravity is so low on Mars and the atmospheric density is so low. So it's really hard to get it going, but once you've started that motion, it will keep bouncing for a really long time. So we can study Mars and study dunes in general using rovers. The Curiosity rover and now the Perseverance rover successfully landed on Mars, which is very exciting, in Jezero Crater. But we also use field experiments. You know, the dunes in Southern California and Eastern California are a perfect natural laboratory for understanding these processes and watching what happens in real time. So a lot of the work that I do with my students in my group is looking at both the very small scale and then looking at the big scale and seeing what happens to these dunes over multiple years as we watch their motion, their migration, and how they change with time. So taking advantage of the natural systems that are right in our backyard is a great mechanism to study these systems and these dune processes and that surface atmosphere interaction. We can also do experiments. So my group has built a wind tunnel here at UCLA, and this is a very preliminary experiment that I ran with my class back in winter of 2020. So right before we went to remote learning. This was, I think, the day before we did that. And so we put ping pong balls in the wind tunnel to represent the low density, low gravity environment on Mars. And you can see that they're rolling here and that there's, some things that aren't quite realistic. But this is a very preliminary first step to an experiment that one of my PhD students is working on, developing our understanding of transport on another planet using experiments and natural representations of these planetary systems. So I'll let it run one more time. It's always good to watch movies more than once. The first time you see what's going on, and the second time it all starts to make sense. So we're going to iterate on that experiment with our wind tunnel and our great group of students. And looking ahead, there are many, many unanswered questions that remain in understanding dune systems. How much erosion is caused by dune sands? One of the projects we're working on right now is to look at how dunes cause abrasion from that wind making sand hit surfaces. How does sand abrasion change as you get closer and further from the dunes? Another question is, how old are Earth's dunes? We don't actually know. It's crazy, but we don't know how old some of Earth's dune fields really are. And then getting back to that, protecting our place in the universe and trying to understand our home in the universe. What will dunes look like in 5 years, in 500 years, or 5,000 years? We want to be able to understand these questions. And so by combining field research, robotic exploration, and laboratory experiments, we are working to answer these questions and plan for strategies in the future. And of course, as a professor at UCLA, one of the great benefits of my job is I get to work with wonderful groups of students. So here's a couple of examples of taking students to the dune fields and doing some hands-on active learning with the sand transport out in the field, which is something that I think is a great benefit of being here at UCLA. So with that, I'll thank you all for listening, and I'd be happy to take any questions.
Wonderful. Thank you, Mackenzie. It's fascinating. So I think at this time we can invite the other panelists to join us on screen, and we can have our audience send us some questions. I don't know, but I think all of us can appreciate that, that in addition to being amazing scientists, you are incredible teachers. I mean, your presentations were so clear and so compelling. So thank you for sharing that with us. So while we begin to get some, some questions from our audience, I thought I'd get things going by asking each of you if you can tell us very briefly, what in your field are you most excited about? What is the most recent development or question that you think is more exciting? I will start with Mackenzie and go backwards.
Ooh, that's a great question. So I study dunes on Earth and on Mars, but we see dunes on all these other places. So one of the things that I'm excited about is understanding how sand moves in wind in arbitrary fluid gravity conditions. I want to know what the physics of sand and wind motion is on Earth, on Comet 67P, and on that exoplanet that we're going to go visit many hundreds of years from now, or maybe sooner. So my goal is to understand everything at a broad scale from that fundamental physics.
Yeah, I can see that. That's really interesting. So Carolina, what about you?
Hi. Well, thank you, Miguel. So I think I'm most excited about two things that are going on right now. One is not my direct field, but there's some technological developments going on right now. It's called distributed acoustic pulsing, and it's going to let us image the Earth inside the Earth at a resolution comparable to going out in the field, essentially. And recently, there's been a study that was able to look at individual floats moving during the Rose Parade using this technique. And to me, that's going to transform the view of the interior, and that's really going to change my ability to then model flow and be able to predict things like topography and the impact on rivers and so on. The second thing is actually related to what I talked about. The fact that understanding the motions of the Earth has an impact on the sea level predictions for the next 20, 30, 50 years. And so I didn't explain it as clearly as I wanted, but without the topography from the interior, if you don't take that into account, the predictions for sea level rise, flooding due to sea level rise in Florida may vary from 1 mile inland to 5 miles inland, which a place like Florida, it's a big deal.
A lot of real estate.
And agricultural land.
That's true. John, what do you think? What is the most exciting thing in your field?
I think one of the most exciting things occurring right now is that the Juno mission is this NASA mission that's in orbit around Jupiter. And I love Jupiter because, one, I've always loved Jupiter, but two, it's got these incredible jet systems. It's got about 30 atmospheric jets like our jet stream, but about 30 of them from top to bottom, from north to south. And these super strong jets have been recently shown by Juno data to extend inside Jupiter by roughly 3,000 kilometers. And that was something we predicted, but nobody really bought it. So it's super exciting that and it's not just me, a bunch of teams were claiming this, including us. And okay, so that's happening. That's amazing. But two, they're now showing that jets are running into where the magnetic field's generated. And so they're getting the best view of any magnetic field, even better than the view we have of Earth's on Jupiter. And it's a crazy field. It's not what we thought. And it's jets running into a dynamo. And for me, that is like dessert mixed with dessert on top of dessert. So it's just the greatest. And that is just years of work.
I can see that totally. Well, actually, we have, that's a perfect entry into the first question from the audience, which is actually for John. And it goes like this. If rotation is what creates the alignment of the magnetic field, what would it flip since the rotation never reverses?
Oh, I love that question. Thank you. So, okay. So one thing you see is the more rapidly you rotate, the more of a fluid gyroscope you get. The more the fluid acts like a big gyroscope, and you get all these little whirlies, and they seem incredibly well organized, and they are. However, it's a word Kenzie used multiple times. It's also turbulent. And so even though it's very well organized by rotation, there's also complexity in those flows. And there's a chance that the core can have a crazy day, right? A statistical anomaly where there's a big, essentially core storm, and that can possibly flip over the field. It's amazing that this can happen. And now I want to answer that at one level deeper. What's really, why I love that question is, in our current numerical models, when we try to make them more realistic, more closely aligned to Earth conditions, the reversals go away. Oh, so you're right. It's such a good question. We actually can't answer that either. We know it's something to do with turbulent phenomena, but actually when we model that, if we're not careful, rotation can turn off reversals. Ooh, so we don't get that yet. This is one of the big open questions. It's one of the ones we're working on.
Sounds to me like there probably are some people out there thinking about studying EPSS that can come and work on that problem.
It's such a good problem.
Yeah. I have a question for Carolina. Is there advection within the lower and upper mantle, not only the convection? Also, when will UCLA have a beach?
Okay, let me answer the first question. Yes, the answer is yes. So, convection in the sense of heat transported by material, that's what moves everything in the Earth, but there's also large scale circulation. So you have advection, just like in winds. So there is a large scale thermal wind in the mantle, if you wish. It's not the same as the kinds of things that John looks at, but we do have motions of this nature. When will UCLA have a beach? Well, hopefully not in my lifetime, because that would be pretty serious sea level rise and pretty serious destruction of LA. What you should know in terms of the planet, right? It's the planet has had periods without ice sheets, right? And periods with ice sheets mean between 120 and probably 200 meters sea level rise. So more than what you saw in my first picture. And at that point, lots of things are, going to be, at one point, North America had an interior seaway. 100 million years ago, there was a sea all throughout the center of North America.
Mm-hmm. Yeah, fascinating. Now I have a question for Mackenzie. What would be causing dunes on an asteroid with no atmosphere?
Great question. So I mentioned Comet 67P. So the asteroid versus comet distinction here is a little bit important. Comets have volatiles, meaning things like water and CO2 that are in ice form. And then as it gets close to the sun, those evaporate and they become gases. So it's the gases that are causing transport to make those dunes. So before visiting Comet 67P, we really thought that you needed an atmosphere to make dunes, but it turns out you just need a little bit of wind. And so the volatilization, the sublimation or turning from ice to gas is enough to move around the dust on a comet and form dunes.
Thank you. I have a question, basically it's for all panelists, so maybe each of you can take a turn. And the question is, what kind of ideal measurement device that is not invented yet would allow you to make major progress in your field? And when we start with that, with Kenzie.
So I'll talk about my favorite upcoming NASA mission because it's not invented yet, but there's people working on it. The Dragonfly mission is headed to Titan, that moon of Saturn, and it's going to be an octocopter that will fly autonomously through Titan's atmosphere and explore the dunes. So it's a double-layered quadcopter with a giant box of measurements, of measuring techniques. And so it's going to be able to take pictures and take samples and tell us about the chemistry of the dunes on Titan. So that one I'm very excited about. It hasn't been built yet and it hasn't gotten there yet, but it's supposed to get there in 2035.
Thank you. Carolina.
Well, I think that's a great question and a really hard one to answer. I would say either being able to drill to the center of the Earth, which is, you should know the Earth is, the radius of the Earth is 6,300 kilometers, roughly 400 kilometers. And the deepest hole is 15 kilometers, right? So if we were able to drill to the center of the Earth, we'd learn a huge amount of information. The other possibility would be mapping the chemical structure of the Earth with some remote sensing technique, which we can't either.
Thank you. John.
You're muted.
You're muted.
Of course I am. It's my job. It's contractual. So Carolina, you kind of answered my question. If we could drill to the center of the Earth, we wouldn't need what I'm going to say. But that's pretty hard to do. And what I'd like to do is just be able to measure the internal magnetic field inside Earth's core. So what we can do is we can measure what's called the poloidal part of the field, the part that emanates from the core. But there's a whole nother vector field. There's a whole nother part of the magnetic field inside the core that wraps around inside it. The part that wraps around inside never has a surface signature. And so whenever we talk about our theories of core physics, people often say, right, but how big is the internal field that we aren't measuring? And we go, well, I have theory for it, but I haven't measured it yet. And the answer is, we need to make a huge leap forward in some form of technology. Actually, technologically, we could measure it, but it's super hard. It may be just as hard as drilling. I'm not sure.
Mm-hmm. Oh, yeah, wow, thank you. So the next question I think is really interesting, right? Because we describe often projects and science that we plan carefully based on understood hypotheses. But someone is asking us, and maybe this is for the three of you, what is the most surprising and interesting finding you've made in your research? Perhaps something that you were not expecting. So why don't we start again with John and then go?
Oh man. Oh, that's so hard. Okay, wait, I'm going to share screen super fast. I'm going to just share screen because I hope this works. We recently did an experiment. Let's see if I can find this, where where is it? It was actually here at the end, where we were doing rotating convection and we started to get tornadoes. I think you can see it in there. There's a tornado in there at the center.
Oh, yeah.
That's crazy. We weren't exactly looking for that. And out of the experiment came tornadoes. And now we've got them numerically and we've got them in the lab, and they break apart along a time scale that's really, everything about these are interesting. And that is a whole new direction for my group, essentially, as we try to understand how these complex coherent structures that really matter in the atmosphere, we have a controllable version, or nearly controllable. We're having trouble actually controlling that thing, but a repeatable way to generate these structures and a really good way to interrogate them. And that for me is an absolutely fabulous direction to go in that I didn't see coming down the pike.
Wow. Yeah. I mean, I just can't imagine the first person, your student who made that observation must have been, wow.
There was some whooping, I believe.
Yeah. Thank you. So Carolina, how about you?
Wait, that's a great question. These are some great questions that people are asking. I guess, and I've been trying to find the movie while John was talking. I showed you a movie of a convective feature where something that was coming up in colors during my talk. Well, once in the lab, we did one of these and then it collapsed on itself. And we didn't expect that at all because, the way you do this, you have a tank, you heat it from the bottom, just like John's experiment there at the beginning. We never turned off the heater. We did nothing, right? The heater was there, was heating, and the plume just boop, collapsed in itself. It just died. And we saw it then after that, we saw it many times and we're still not sure what it is.
Wow, fascinating. Thank you. Kenzie.
This is a great question. So I say to my students and at conferences all the time that Mars is a wind-dominated planet, and there's no liquid water on Mars today, and so really wind is the main thing that's changing the surface. So I've been working on a project with a student that we just finished, and 7 years ago, Curiosity drove across a really small dune, and in the satellite images of that area, you can see the tracks going across the dune, and it was very dusty. So the tracks show up really well. And since then, there's been 2 major global dust storms, and it's been 6 or 7 years. And looking at images today, satellite images today, you can still see the tracks. They're still there, even almost a decade later. So our most recent really surprising discovery is that even though Mars is this wind-dominated planet, there are parts of Mars that are very, very stable, and where the tracks from the rover are just not moving, and there's just not enough wind or activity to wash that out and resurface everything.
Well, thank you. So much exciting research to be done, really. This is probably the last question, but this question is from a parent at the Science Academy STEM Magnet in North Hollywood, who would love to hear from each speaker how they got started in their field, and if each could comment on an influential teacher or mentor they had. So let's start with Kenzie.
So I started out as a physics major in college. What I thought was physics is actually mechanical engineering. So I wasn't quite in the right fit for me. And I tried a couple of different things. And then I met this one professor and I told him that I was really, really interested in planetary science and I wanted to study Mars. And he said, "You are in the wrong field. You're in the wrong major. Come take my geology class. This is where you need to be." I study Mars. And so I took it and I love it. And I never went back. I just took all the geology classes and majored in that and then got my PhD and ended up here at UCLA. So that one kind of chance encounter with a great professor really put me in the right spot.
Thank you. Great story. Carolina.
That's a really hard question for me to ask because I think I just had so many people that supported me along the way. I have a very peripatetic career in the sense that I wanted to study archaeology and then I changed to geology and I just loved plate tectonics. And so I went to study that in grad school. And then I started studying that and we were doing a lot of field work and it wasn't quite my thing. And then the professor gave a talk precisely about how these structures that you see in the lab generate changes in the shape of the Earth. And I said, that's what I want to do. And so he arrived at Berkeley, and I think, just transformed this idea that you could couple the physics with the geology. It just, blew my mind. And since then, I think that's what I've been doing. And but I've been very fortunate of having lots of supportive mentors along the way.
Well, thank you all of you for sharing this part of this particular the answer to this particular question, but also for really having us, taking us through an hour of really exciting, interesting science. I think these are amazing work that you're doing. So we're really very grateful to you for sharing that. So again, I'm very grateful to John Erno, Carolina Litko-Bertoloni, and Mackenzie Day. You're our UCLA superstars, some of many. And I also want to thank all of you who have joined us today. I think this has been an incredible event. We will be having events like this with some regularity. Our scientists, our professors are really eager to share with you the discoveries, the work that they do with many, many, many talented students. We encourage you to visit the EPSS website to learn more about this research and much more. And we look forward to inviting you to future departmental events. And I also like to thank the organizers whose squares are a little bit quiet through the talk. So again, thanks everybody for joining us today. Have a wonderful rest of Thursday and a wonderful coming weekend. Bye-bye.